We're coming to you from the CINA Center at George Mason University. We're so pleased you can join us for today's talk. This is part of CINA's Distinguished Speaker Series. So our speaker today is Professor Robert Simon of George Mason University, and his talk is titled, "You Cannot Always Hide: How to De-anonymize Bad Actors on the Internet." Before we start, and before I introduce Professor Simon, I'd like to share a few words about CINA. CINA, C-I-N-A, stands for Criminal Investigations and Network Analysis. We're a DHS Center of Excellence hosted by George Mason University. Our mandate is to further DHS and the US government's mission to counter transnational organized crime. And criminal investigations and network analysis are our signature techniques to do that. Professor Simon's talk today touches on several of CINA's research themes, including criminal investigative processes, criminal network analysis, and network analytics. Now, in case you're not aware, DHS Centers of Excellence are managed by the DHS S&T Directorate's Office of University Programs. They're led by universities to, quote, conduct groundbreaking research resulting in rigorous, objective knowledge products and timely solutions for DHS components. So I know that we have a lot of folks on the line today from DHS components, as well as from headquarters and from S&T in particular. And we want to emphasize that this is your research, and we want to make it as accessible and mission relevant as possible. Today's Distinguished Speaker Series is special because sometimes we do bring in outside experts, folks from industry who talk on more general topics, but today's speaker, Professor Simon, it will be presenting research that in part was developed through an award from the CINA Center at George Mason University. So it is particularly close to our mission and hopefully to yours. Now, CINA is supported by a DHS board of directors who help us to ensure the relevance of our research and identify champions and fundings for potential transmission. So if you're excited by what you hear today and you think that CINA research can help your mission, please put your email in the chat or respond to our follow-up survey or visit our website at cina.gmu.edu to join our mailing list. We're always happy to set up capability briefings with DHS and other US government stakeholders in the hopes of identifying champions for eventual knowledge and technology transition. So now I'd like to introduce our speaker. Professor Robert Simon is a professor in the Department of Computer Science at George Mason University's College of Engineering and Computing. Professor Simon's research specialization is in the field of networks, mobile and wireless computing, performance modeling, and simulation. He teaches undergraduate and graduate courses in these areas as well. Professor Simon received his bachelor's degree in history and political science from the University of Rochester and his PhD in computer science from the University of Pittsburgh. Professor Simon is an active member of CINA Science Network here at George Mason University. In fact, as I alluded, along with his co-PI, Assistant Professor Eric Osterweil, Professor Simon is currently conducting a CINA research project on time series analysis of anonymized communication channels, which he'll talk about during this presentation. Now, a quick note before we start. Professor Simon's exciting title will not disappoint. However, the word de-anonymization here only describes potential applications of his approach to operational contexts. Consistent with the terms and conditions of CINA's award from DHS S&T's Office of University Programs, Professor Simon and his collaborators developed the techniques he'll describe today using only synthetic data. In other words, his research did not implicate personally identifiable information of any real individuals. There has been no exchange of data between the research team and DHS components. Now, without any further ado, I'll turn over the floor to Professor Simon.
Well, thanks a lot, Brooke. So I am going to talk about de-anonymization, but before we talk about that, we actually need to talk about anonymous communication. And so anonymous communication means different things to different people, but we're approaching it from the perspective of a computer network, I'm a computer scientist, and so that's sort of what we think about. And so one interesting question is, why anonymous communication? And there are really good things about it and really bad things about it. So among the things that are good about it is actually, if you look at the origin of anonymity techniques in computer networking. In many ways, the stuff that we're doing now was developed 25 or 30 years ago. In fact, a very important piece of anonymous communication technology is called Tor. It's kind of like the great grandparent of a lot of current networks out there. And I always like this quote because one of the original motivations for developing Tor was to do things like provide open access to folks, let's say, who are in some kind of repressive society. So it was actually pretty interesting. So anonymous communication could be really good, but it could also be really bad. So it can be bad because of things like the dark web, botnets, and I think what a lot of folks here are interested in is, of course, transnational criminal organizations. So let's talk a little bit about actually what's out there. So if you look at the growth of applications for anonymity, there's been a staggering increase. And so these statistics that I'm showing you now are kind of self-reported. So for instance, I have the growth of Telegram here. Probably a lot of you have heard of Telegram. I don't really know how accurate this is, but if nothing else, they're reporting a growth of almost from 35 million to 800 million over a 10-year period. So that's an astonishing increase in terms of popularity. If you look at also at the most downloaded apps, I think this was from November 2023, out of the top 10, 3 of them are very specifically used for, among other things, anonymous communication. So that's again pretty impressive. Now, all the apps up here have some level of security, but whereas 10 years ago, if you told an average user, well, I do end-to-end encryption, their response would be, who cares? Now, end-to-end encryption, even if not everyone knows what it is, it's kind of gone into the lexicon, right? People know that it's some kind of buzzword. So that's actually is pretty good. Of course, what's happening is that these are now state-of-the-art ways of getting anonymity. And I'm going to give you a more precise definition of anonymity in a moment, but let's just call it anonymity. From a technical perspective, the way that folks get anonymity is to use a series of technologies that we call PPTs, privacy preserving technologies. And the reality is, as you just saw, and as many of you know, these are available to most internet users. So you don't have to be particularly sophisticated to download a WhatsApp application and get some level of anonymity. So what it means also is that bad people can use it, and they can use it in a variety of ways and for different purposes. So one of the things that we would like to do is develop tools that enable folks, for instance, in law enforcement, to be able to go out and find a bad actor. And as you're going to see, what I really mean by that is not, they live in a certain apartment building, though you might be able to tell that, but really to kind of localize a bad actor to a specific IP address. An IP address is the network name of where a computer is. Why is that important? Well, you can trace their activities, and in some cases, in many cases, you can actually geolocate where they are. And so that's maybe a tip-off. So the point of this talk is really to show that just by looking at computer network traffic, even if you can't crunch through the PPT, you may in fact be able to find a bad actor. So to be a little bit more specific, let me just give you a couple of scenarios here. So it might be the case that there's some kind of nasty message board out there. So you can think of something like through the dark web or whatever, and people post on it, and they typically post anonymously. So you might have some user that identifies as Evil Robot 26, and Evil Robot 26 is periodically going on this website and posting stuff that is distasteful, is illegal, it's not good, right? So it's certainly possible that there are analysts out there, law enforcement, other kind of authorized agencies that are actually looking at the nasty message board, right? They may have no idea where Evil Robot 26 is, but they do know that there's some kind of behavior that Evil Robot 26 is doing that's sort of bad. And if Evil Robot 26 is even a moderately sophisticated user, not state level, but moderately sophisticated, they're using some kind of privacy preserving technology to hide where they are. So the easiest thing to do is just call yourself Evil Robot 26, but they might be doing something else. And we'll talk about what those other things are. So what we would, again, like to be able to do is provide tools that we could give to someone who would use it as a tip-off. They know who Evil Robot 26 is, and I'll show you the kind of information that they need. And based upon some of their tools, it would sort of narrow down, if not specify, where Evil Robot 26 is in terms of the wide internet. So here's a more specific example of where we think this kind of work can help. There's something that's often called persona tracking. So you might have a user that during the day logs on as a friendly little penguin named Tux, and what Tux does is he looks at kitten videos or whatever, and then in the evening, the same person comes in as Evil Robot 26, but in fact they're the same person using the same IP address. So if we can de-anonymize where this is coming from, we may in fact be able to also do something like do persona tracking and figure out that, well, you know what, Tux also has some behaviors which may be also of interest, and we have kind of localized them to the same machine, the same basic IP addresses. So there's kind of like a lot of stuff on this diagram, and the thing on the right says DNS protocols. DNS stands for domain name system, so probably some folks have heard of it. I'm going to go through it because DNS is going to turn out to be a key enabling mechanism for how we think we can actually do de-anonymization. Okay, so we really need kind of like a slightly more formal definition of what we mean by anonymous communication. And it's very much tied up with this notion of privacy. And so privacy, for depending upon the environment that you're working, means different things for different people. But for kind of computer networking people, for computer scientists, for information security people, when we think about privacy, we think about the technologies and the techniques and the methods that we can use to actually maintain privacy. What does privacy mean? Well, privacy in some sense means that the user has some level of control over who gets to see what. It can either be that you can't read what I'm sending because I'm keeping it confidential, or you don't even know who I'm sending it to, or you don't even know where I'm coming it from. That all being said, there are a variety of different techniques. We're going to need to understand those different techniques. But in general, what we refer to that collection of techniques as somewhere in the CIA triad. So it's called CIA, nothing to do with the Central Intelligence Agency, it just so happens it's the same acronym. So what this means is confidentiality, integrity, and availability. Confidentiality means like data hiding, means like things like encryption. There's no PII leakage. If you can get perfect confidentiality, then basically you're private and you're safe. So integrity means that data hasn't been changed. From a low-level technical perspective, this is accomplished by things like cryptographic hash functions. It doesn't matter, if you've never heard of it, it doesn't really matter. It just is a way of basically showing that your data has not been changed. And availability, well, availability means that the system is always there. It's always available. If you can do all of these things, you have a pretty good system. Anonymization in a computer network, Evil Robot 26 not being able to be traced to where they are, is because there's some combination of the different techniques and technologies that go into the CIA triad. So in order to understand this, and in order to understand what we're proposing, we have to look a little bit at the fundamental part of actually how computer networks really work. So from a high level, and of course, this is a dramatic simplification, and if the folks already know about networking, kind of rolling their eyes a little bit now, but just bear with me for a second. So here we have some angry robot who is typing some tirade and going into a message board. And so the robot is sitting there typing away, and then essentially the computer or the mobile phone or whatever is kind of chunking up all of that information and shooting out information packets into the network, into the internet. And so again, this is a gross simplification, but the way that we're going to think about de-anonymization is we want to do it at the internet level, or what's sometimes called the network level. it's a kind of a confusion of terms. So there's a network stack, and then there's a network level, and these are all IP packets. So what's really happening is that as you type in this angry diatribe, this angry screed, and it happens to be the Premier League because I didn't tell ChatGPT that I wanted an example for the NFL, so it defaulted to the Premier League. That's fine. What it does is that it chunks up that long message into individual discrete packets. And the way that the internet works, for the most part, is that all of that data, in this case, the text message, is put into a data structure, an IP packet, and there's a lot of metadata that's there. And what the internet will do is that it will use the data on a packet by packet basis, the metadata in the network header, to get it to go from evil robot 26 all the way to the message board. Now, it's this packetization is kind of the bread and butter of people who do computer networking and information insurance. Most users kind of neither know nor care about it, but we are going to care about it because it's the way that packets appear in the internet that we think will provide enough information to do the de-anonymization. So let's talk a little bit more about the stuff in the CIA triangle here. So let me talk a little bit about confidentiality. And this is kind of a massive topic. And what that means, for the most concretely, what it means is that we care about encryption. And what encryption means is that you have some kind of data and it's scrambled. And so no one else can read it except the intended recipient. And so when folks do design secure systems, when they do information assurance, and they think about it from the point of view of the computer network, they typically make the following assumption. They assume that every single packet is being eavesdropped on, it's being sniffed. And so no matter what you do, as soon as it leaves your computer or your phone, someone else can look at it. And so the protections for privacy, the protections for PPTs, for CIA, are dependent upon the fact that even if that packet is sniffed, no one can read it. So let's talk a little bit about encryption. In general, there are two basic ways of doing encryption. One is called symmetric, the other is called public key. They all revolve around very complicated mathematical algorithms, and they all require, in some sense, a secret key, or at least one secret key that is shared between the sender and the receiver. So the fundamental security of encryption depends upon the type of encryption algorithm. These are very secure, so it's unlikely that the average user, and in fact, it's unlikely that anyone can really go ahead and quote unquote crack an encryption algorithm if it's well designed. The security depends upon the security of keeping at least one of the keys secret and safe. And so in this diagram here, the sender and the receiver have somehow agreed upon what the key is. It's secret and safe. So the message is going through. Essentially, the robot types it in. The crypto, using the key and whatever algorithm they're using, it doesn't matter, will encrypt it, will make it gibberish. The inspector who sees the packet can't read it, even if they know exactly what crypto algorithm they're using because they don't have the key. And at the other end, the receiver decrypts it by using another key, maybe the same key, depending upon the type of crypto, and the message works. And this is how you get confidentiality. So another critical part of privacy-preserving technologies are basically secure protocols. And so the diagram on the right is typically a way that we write what a protocol is. A protocol is simply a set of rules for a sender talking to a receiver. So the arrows show essentially the different messages that go back and forth. The details here don't really matter. The important part is that virtually everything in the protocol that you see is merely meant to set up a secure association between the sender and the receiver. And the outcome of this secure association is the establishment of a shared cryptographic key. The assumption here is that, once again, the inspector sees all of these messages. They know what the messages are. Typically, the secure handshake is not encrypted, so the inspector knows what it is. The inspector knows what they're doing. Even with all of that information, they can, for the most part, not derive what the shared secret key is. So there are many, many protocols out there that do this. Those of you who work in networking information assurance have heard of some of them. Probably all of you know the difference between HTTP and HTTPS because you're made to do it. There are a whole bunch of them out there. And again, if they're well designed, they will not leak information even if the inspector is seeing all the packets that go back and forth. So the crypto, for the most part, is secure. If the protocol has been implemented correctly, it also is secure. So that's a pretty powerful range of tools out there that will give us some level of PPT. So we need to talk about a couple of other things. Many of you have at least heard of what an IP address is. An IP address, or Internet Protocol address, is really nothing more than a bit string that enables the Internet to go how to take a packet from the sender to the receiver. So when you shoot into the Internet, there are a lot of different routers out there. It goes through a lot of different hops. One of the design features of the Internet is that each packet is kind of self-identifying. And so essentially what a router will do deep inside the core of the Internet is that it will look at the IP address of where the packet is going to and then make a decision as to where to forward it to the next hop. Now, what's sort of interesting about this is that Internet addresses at some level cannot be completely hidden. And that's going to have a very important implication for us, but at some level, it can't be hidden. So in the example here, the IP address of the robot is 192.168.1.1. It's just a bunch of bits that routers can use. And that in sending it to the receiver, which 192.168.20.21, and what the inspector in this particular case will see where the IP address came from and where it's going to. So in this particular case, while the inspector could not read the contents of the packet because of the way this communication is set up, the inspector can instantly tell where it came from and where it's going to. So the kind of anonymity here is simply the content of the message is kept secret, but the sender and the receiver are exposed. And so this is not necessarily the anonymity that we want. We want to think about it from the point of view of Evil Robot 26, where Evil Robot 26 doesn't want anyone to know where they're currently located in the world of the Internet. So let's talk a little bit about anonymous communication. So this really means that you don't know where it's coming from and you don't know where it's going. There are many, many examples out there of anonymous communication. I would speculate that probably everyone on this call who at least is using, that does something from home for work, is using some kind of virtual private network. There are many, many other ways of doing this. There are kind of end-to-end messaging services. There's this network called Tor, which hides the sender and receiver, which we're going to talk about in a second. They sort of work in different ways. But to kind of summarize it a little bit, the picture that you see here is pretty good representation. So here we have the robot on the left talking with the collaborator on the right. And what they really want to do is to hide where they're coming from and where they're going. And so in this particular case, they're using a VPN. It could be something else. And what a VPN does is essentially takes a packet with the sender and the receiver and encapsulates it into something else. And the something else essentially will have a source and a destination, but the ultimate sender and the ultimate receiver are going to be hidden from the inspector. And so in this case here, what the actual robot is doing is sending it to some kind of security gateway. This can be anything from the VPN that's running on your laptop to something in your organization to one of the million VPN services that are out there. What the VPN security gateway will do is essentially say, okay, I see where you're coming from. I see where you're going. I'm now going to encrypt the entire packet, including your IP source address and where you're going, into a new address. And so what it looks like from the inspector is the IP address of the two security gateways. So all that the inspector can see is the security gateway talking about the security gateway. The inspector has no idea has absolutely no idea where it's actually coming from or where it's going to. When it hits the security gateway, assuming the inspector can't see in the inside of where the gateway is protecting, it rips off the outer layer and figures out where it actually needs to go, and then the packet winds up being delivered there. So this is anonymous communication. There are other examples. So an important one to know about is something called onion routing. In the original Tor network, and there were kind of many variants of Tor, but Tor stands for the onion router. Essentially, you take this idea of a tunnel and you kind of keep extending it. What you do is you put tunnels inside of tunnels, inside of tunnels, inside of tunnels. And the advantage of doing this is that even the routers in the middle, they don't know where the packet came from, and they don't know where it's going. So if you look at the diagram on the left, there are encrypted packets inside of encrypted packets inside of encrypted packets. So essentially, when router B gets it, for instance, something in the middle, it can kind of peel off a layer and it can see where the packet needs to go to for the next hop, but it doesn't know what the ultimate destination is, and it doesn't even know where it came from. So the idea is like the onion, you keep peeling it so you have tunnels inside of tunnels inside of tunnels. And so VPNs inside of VPNs and tunnels inside of tunnels is kind of a common way of doing all kinds of security. If you talk to IT folks in many large organizations and you say, well, what actually happens if you look at a network pipe coming in, a lot of times they will say, you know, there's so much encryption inside of encryption inside of encryption inside of encryption. There's barely any space left for the actual message. And so this is kind of an ongoing issue. If you're worried about security, you just kind of throw another tunnel at it. So tunnels are good. Okay, so let's talk about now how what we're going to do. And so let's start with the assumption that no one's going to break encryption and no one is going to break a secure protocol. So is there any hope of doing any kind of de-anonymization? If you're looking at network traffic and only network traffic, you can't break crypto, you can't break protocols, what can we do? So one thing that we can do is we can figure out kind of like what's the average life cycle of anyone almost doing anything. So if you look at the diagrams here, the actual internet, which is massively complex, it's beyond human understanding, but there is some level of structure to it. And one way you can think about the structure is that there are all different types of internet service providers. And so however you're listening to this, I'm standing here in my office and you're wherever you're at work or at home or whatever, but we're all using different internet service providers. And so we're bouncing through different types of networks. And so Comcast may have absolutely no interest in telling anyone in this room what's happening on their networks. But believe me, Comcast knows what's happening on their networks. So one of the underlying pins is something called DNS, which I'm going to talk about in rather great length in a moment. But what actually happens is, independent upon whether you're doing privacy preserving technologies, whether you're doing anonymity, you need to talk to DNS. And so the thing on the left shows the browser person, the robot, whatever it is, goes up to, it needs to get some kind of information. And then once it gets this information, talk about it in a sec, it then goes ahead and will go hit the server at the bottom of the page. If the user, the evil robot, the Tux, whatever it is, if they want to use anonymizing networks, then they go through the anonymization service, but that anonymization service at the other end will still need to, at some point, to go and talk to DNS. And so the traffic between Evil Robot 26 and the Nasty Web thing may be going through the anonymizing technologies, but there is one thing that they share in common, which is they need to talk to DNS. Okay, so what is DNS? Well, DNS is, it's no exaggeration to say that DNS is one of the foundational underlying underpinning technical mechanism of the entire internet. And the reason why is that it takes a human readable name, www.gmu.edu, and it maps that into an actual IP address. So you need, when you type in www.gmu.edu, CINA.edu, whatever it is, the computer network doesn't know what that means. What it does know is an IP address. And the way that it gets that information is by using DNS. DNS, you can think of as this massive global distributed database. It's a hierarchy. So what it means is at the very top, essentially, The servers at the top know everything, or at least know where the information is. And then as you go down the hierarchy, either your local DNS cache server will know where it is, or knows who to ask. So it's been around forever. Kind of the lead technical organization for the internet is called the IETF. And the IETF has been worried about security since the birth of the internet. It's a different discussion. And many years ago, they came up with a standard called DNSSEC, which was specifically designed to make DNS secure. So the beauty of DNSSEC is that it works. The disadvantage of DNSSEC is that it doesn't provide, at least in the original specification, there was no confidentiality. So for several reasons, a bunch of reasons, not the least of which is DNSSEC, at least as originally proposed, didn't provide confidentiality. There's been a long ongoing desire to add PPTs, privacy preserving technologies, into DNS. And the way that that works in many ways in practice is because the DNS now uses secure protocols. One example is DNS over HTTPS, which is known as DO. DOT is another one. So what's the traction of this is secure, it's encrypted, can't see what's happening, and it's now widely used. And so pulling out this statistic here, so Chrome and Firefox enabled DNS over HTTPS by default. And since they account for about 68% of the market, what it means is that DNS is privacy preserving technology in DNS is now becoming a real thing. However, as my colleague Eric Osterwald likes to say, DNS is not, as a privacy PPT, it's not a panacea. It doesn't solve everything. And the reason why is because even if the information is encrypted, it turns out that when you hit DNS, there's a certain behavior of the packets, a certain pattern of life of those packets of that DNS request that essentially may in fact leak some kind of information. So it's this pattern of life that kind of underpins the results that we want to get, which is ultimately de-anonymization. And so confidentiality is fine, it's perfect. I'm not going to break it. I don't think you guys are not going to break it, but it might mean that the sources are traceable. So what do I mean by pattern of life? So let me give you a very simple example. Actually, before I do that, let me give you a thought experiment. Suppose you could actually get computer packet captures from all over the internet. So you could look at DNS, you could look at Comcast, you could look at anything you wanted to do. This, of course, is impossible. Even if you could, there's too much data, et cetera, et cetera, et cetera. But it's an interesting thought experiment because if you could get at least some of that information, could you in fact do pattern of life, which would lead to some kind of de-anonymization? So the thought experiment that we are doing is to see what amount of information you would need to get to figure out what the pattern of life is, assuming that you can't break the encryption, which you can't, and you can't break secure protocols because they're well designed. So let me give you a very simple example. So here's from my laptop. I put a packet sniffer on it, and I just sat down and I watched some YouTube video and I listened to Spotify. And what the graph is time is on the x-axis, and this is the number of packets on a second-by-second basis. And so, for instance, if you look at different times, there are an awful lot of packets that are being sent out. And a lot of times, nothing is being sent out. It's not necessarily super interesting, but what it does show is that the information is very, very bursty. So it's not like a nice uniform level of how packets go. There are these bursts of intense activity that are followed by nothing, followed by intense activity, followed by nothing. So in some sense, there is a pattern. And again, I'm showing you an example, so mathematically doesn't prove anything, but I just ran the same experiment like 4 minutes later, looked at the same YouTube channel, let's listen to whatever Spotify channel it was. And in fact, if you look at them side by side, again, this is mathematically showing nothing, but if you just eyeball it, right, they look sort of similar. It looks like there might be enough information where you could match these two things to say, hey, this is coming out of a certain computer, and the person's probably doing the same kind of thing. So the pattern of life shows that you may be able to figure out, it's a fingerprint basically, right? It's some kind of fingerprint for either my computer or kind of what I'm doing or something like that. So that brings us to the discussion of the CINA DHS project that we're starting to wrap up. So Brooke kindly described it at the beginning. This is joint work with my colleague Eric Osterwald and some of our graduate students. So this is our approach. So we take this, our conception of the internet, which is all these green circles, and we know that at some point public DNS needs to be used. So you type in www.nastymessagingboard.com and you hit return, and in the blink of an eye, you go to the nasty message board, right? But actually what's going on is that at some point you're hitting public DNS, and then we know that they're at nasty message boards. And the way that we do that, packets have a lot of information. We view them as what's called the time series. The time series is nothing more than a set of events in time. Each packet has a timestamp on it. It has a lot of different features, a lot of different fields, and we use techniques from statistical machine learning. In particular, we use techniques in time series analysis. We can, if you're interested in that, we can discuss that during the Q&A or offline. So we play with a lot of different techniques. We sort of have a good idea of what techniques work and which ones essentially don't work that well. But among the things that we learn is what you need, what you need to do and what kind of sensors you need to do to get it to work. So the first step is to kind of take these green circles here and map it into something that you can actually capture packets on. And so we have this kind of rather complicated diagram here. This is actually the virtual lab that we set up in a laboratory. It's important to spend a little bit of time to actually talk about how we're doing this. The pattern of life, our understanding of pattern of life is very contingent upon getting, what it would really look like. And so this is not as hard as it seems, even though it's a virtual laboratory. And the reason why is for things like DNS, we can run actual DNS, the actual software that runs DNS. In terms of the ways packets work, we can actually run something that very faithfully emulates the way a router works. And so, if you're interested in in the needle in the haystack, right? We're interested in the needle in this case being Evil Robot 26. You need to generate an awful lot of background noise. You got to kind of saturate the system. And that's actually possible to do inside of a virtual environment. And so we've mapped kind of these kind of scopes, and this kind of shows the different nodes we generate. An awful lot of traffic. We run the pattern of life, and the results under some circumstances you can see have been actually very, very encouraging. So this is what our virtual testbed looks like. In practice, if you wanted to use this, we kind of developed, relatively speaking, a kind of a crude interface to enable an analyst or an operator or user to kind of do this. So the operator may in fact know that we want to get something called Evil Robot 26. And so if you type in Evil Robot 26, well, we call it group 0, user 0, because this is how we're running the experiments. It will rank order a set of IP addresses and show you more or less the confidence that it has as to that Evil Robot 26 is at this IP address. The column on the left is really more for engineering usage. For those of you who've kind of dabbled in the machine learning space, you know that something called explainable AI is very important. And so what this shows is kind of on what basis the machine is making its decision that it has enough confidence that the most likely IP address is whatever is ranked number 1. And so this is, this is important for doing any kind of forensical analysis. The analysts may not care about this, but it does kind of provide background information. So in our lab, we've developed a kind of a computing infrastructure. So we have something called our Docker Swarm. Details aren't important, but we feel like we've designed it in a way that we kind of have a small amount of computing power. Other folks probably have more computing power. So it will kind of automatically kind of adapt to what's actually out there. And, you give us small computer, we'll get something done. You give us a larger computer background, we can ingest a lot. PCAP files, packet capture files, are humongous. The scale that we're talking about is mind-boggling, and so you're not going to run this on your laptop in 2 minutes. You want, if you have access to computing power, you want to actually go ahead and do this. It will automatically batch it into different types of patterns of life, and then we do the machine learning. So a reasonable question is, well, how do you know that it's actually working? And so we want experimentally validated. This is it's not a theoretical exercise. You either prove it experimentally or you don't. As Brooke mentioned, we don't have any real data. So we needed to come up with some way of generating synthetic data. And so we were confident that the pattern of life in the computer network was fairly accurate because we're running the real software, running it on real machines in the Docker Swarm. And so we needed some way of kind of generating a workload. And so what we simply did was many, if not most, social media social networking sites publish anonymized message logs to show how much traffic they have. So you can't see the real users, you don't see the real IP addresses, but they just kind of go ahead and say, this is group 26, and here we have user number 1. So what we did, this took a while. We took this anonymized log of a well-known user group. It was close to 1 million different anonymized subgroups on different topics. Don't really know what they are. And then we just would randomly pick a group, and we use that to generate actual computer workload. And we ran it under a wide variety of network topologies, a wide variety of configurations with a wide variety of privacy-preserving technologies, different types of encrypted DNS, no PPTs. So we compared how well we did, and we also compared our results of similar research. And the bottom line is under many circumstances, we did pretty well. It's a little bit difficult to read this graph, and I promise you this is the first and last graph that I have here, but you want to get pretty high accuracy. What this shows is accuracy means that we nailed it perfectly. Recall at 2, 4, and 8 means that we correctly narrowed it down to the top 2 or 4 or 8. And so what the different bars here show essentially what type of scopes we had access to. So the ones on the left, we went all the way up. We had access to a lot of different sensor information, a lot of those green circles. If you have less information, the accuracy goes down. In many cases, it's not perfect, but even in those cases, it might actually be a good tip-off for an analyst. So we are approaching the end of our project. We do have open source software. It's on a GitHub page, which we periodically update. We have an online paper, and because we're academics, and so we're constantly trying to produce new papers. We are planning to push out a brand new set of results in a brand new paper next month, and we will probably post that as well. And then finally, I do want to point out that there's been 30 years of work in anonymity in communication systems. And so we are by no means the only research group that does this. De-anonymization is a fast topic. So here's a very small subset of work that we found useful. So if you're interested in reading more about the kind of research in this area, or figuring out what else other folks are doing, not just us, here's kind of like a beginning subset, and a Google search will give you probably 1,000 more papers. So many thanks in particular to DHS for funding this work. Thanks to the CINA team, which has been a true joy to work with. They've really helped us a lot, and profound thanks to Eric, to Taylor, and to Pavan.